Section 9.8, we're going to be taking a look at power series. So this is a kind of a continuation of what we did with 9.7, where we did Taylor polynomials and Maclaurin polynomials. So as we saw in 9.7, functions like f of x equals e to the x can be approximated by polynomial functions. Now we can expand this idea to find an exact representation of an infinite series, which is called a power series. Here's what a power series is defined to be. If x is a variable, then the summation from n equals 0 to infinity of a sub n x to the n looks like this, right? This is called a power series. More generally, we can talk about a power series centered at any general value c, and instead of just having x to the n, we have x minus c to the n. And we call this a power series centered at c. And that looks a lot like what we did last time, but the notation's slightly different. So when we were working last time with Maclaurin and Taylor polynomials, we had some subscripts like p sub n, right? So p sub 4 or p sub 5. So we would do this series out, but we would actually stop it. Much like back in section 1, we looked at s sub n for a summation that stopped at a particular point. And then after we did that, we said, okay, but what if we do it for, like an infinite number of terms? This is the parallel. We're doing this for an infinite number of terms now. So these are a couple of examples, not ones that we have to do anything with, but I just want you to see what they look like. So the first one right here is a summation from n equals 0 to infinity of x sub n over n factorial. And if we were to write this out, we saw this one last time actually, or at least a variation of this one. It would look like 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. This would be a power series. Where is it centered?
0.
This is a power series centered at 0. And as you look at this, or as you sort of think about this, what you should be noticing is that, with the exception of the x to the n part, right, if you ignore that portion of it, this over n factorial, we've dealt with problems like this in our infinite series sections before this, right? From 9.2 to 9.6, we were dealing with stuff just like this. It just didn't have a variable x to the n in it. So there's a variation that we're going to have to deal with because of that. But be aware, this is not altogether different than what we've been doing. Okay, the next one is the summation from n equal 1 to infinity of negative 1 to the n, x plus 1 to the n. And it looks like this. So my a sub n in the first example has to do with it being, well, it's the 1 over n factorial, right? My a sub n in the second example is the negative 1 to the n. If you compare it back to the example over here, there's an a sub n that gets multiplied each time, right? And that's what's changing. So the x to the n, or the x minus c to the n, that part is new. The other part's things we've done before. So this is another power series. Where is this one centered?
Negative 1.
Yep. There we go. Power series. Centered at negative 1. Okay, so we just wanted you to see what they look like, and that they really look quite similar to what we've done before with this variable component that's involved now, and we need to see what it does, and what does that, how does that affect things. Okay, so our next theorem actually talks about what that means, that variable component. This is theorem 920. For a power series centered at C, precisely one of the following is true. One option is the series converges at only C. Okay, so in our previous examples, maybe it converges at only 0 or at only negative 1. Option number 2. The series converges absolutely for the absolute value of x minus c that's less than r, and diverges when the absolute value of x minus c is greater than r. So in other words, it's converging on an interval. There's a space with in which it converges, and outside of that space, it's not going to converge. Okay, there's certain values that work and certain values that don't. And the third option is that it converges absolutely for all values. What sort of seems or feels like it's missing?
Just diverging.
Just diverging. So these will always converge somewhere. Did you catch that? Always converge somewhere, either at one particular point, an interval of points, or on the entire number line. One of the three is going to happen. So the location where it's going to converge, R, is called our radius of convergence. Okay, what is the radius for which this converges? In case number one, so if you go back up on your page over here, right here is this is my case number one. In case number one, we would say that R is equal to 0. It only converges at a point, then there's no radius, right? It's a 0 radius. It's just converging at one point. And clearly, in case number two, although it's not listed here, you can see how you would find the radius. It's related to this x minus c factor and the distance between R. We'll see an example of that one. And the last one, case number 3, we would actually say that the radius is infinity because it converges everywhere. So it's a radius that's infinity. The set of all values for which the set of all values x for which the power series converges is called the interval of convergence of the power series. So obviously the interval of convergence and the radius of convergence are highly related ideas. They connect to one another. They'll go hand in hand. And I believe that when we were on the boards that Noah was talking about how much he loves the ratio test. That's his favorite one. So when I was working through all my slides and stuff for this lesson, I actually thought about you because you're really going to like these examples because you're going to be using the ratio test. Nice. Okay. So the ratio test is heavily used to doing these. Okay. So we're going to find a radius and interval of convergence for a power series. Remember, they're always going to converge. We've just got to figure out how much of a convergence we have, kind of a feel. Okay. So if you take a look at this, these are always going to bounce back to the ratio test, which we learned, and we liked that one, at least Noah did. He's the only one that's told me. But we're going to use the ratio test. So using the ratio test, we're going to take the limit as n goes to infinity, and we're going to do the ratio here. So I have a sub n plus 1 over a sub n, right? That's the ratio test. So this is the limit as n goes to infinity of n plus 1 x to the n plus 1 over 2 to the n plus 1. And then this would be over the same thing that I've got in my original piece. So instead of writing it as division, I'm going to write it as multiplying by the reciprocal. So it would end up with times 2 to the n over n x to the n. Okay, everybody good so far? Ratio test is fabulous, isn't it? Do you see some things that are going to reduce here?
Yes.
Sure hope so. So, Adeline, what do you see that's going to reduce? Tell me one thing.
2n and n plus 1 and 2.
Okay, so the 2n plus 2, or 2 plus 1 on the bottom, and the 2n on top is going to be canceled to a 2 on the bottom. What else do we see? Somebody else tell me something.
X to the n, next to the n plus 1.
Awesome. For the same reason, right? Okay, so the x to the n and the x to the n plus 1, and I'm going to be left with an x, in this case, on top. Okay, is everybody good with that? Okay, so let's kind of write what we have left over now. So we have the limit as n goes to infinity of the absolute value of n plus 1 times x over 2 times n. Okay. Notice, I need absolute values here. I actually really need them. I can't just disappear them like I did a lot of the times with the other problems we were doing because we don't know what x is, therefore we don't know if it's positive or negative, right? If we just were looking at n, a lot of the times everything was already positive and the absolute values are sort of irrelevant. They're necessary here, okay? The other thing that's necessary here is that we have this tendency to just say, well, I know what this limit is and move on. Well, Well, we can't do that here because I've got this variable involved, so I actually have to like show it out for real. So when we were sort of intuitively saying, oh, look, this is really going to go to, well, I can't do that here. I actually really have to multiply by the 1 over n and find the limit, okay? So if I do that, I'll end up with, so the x and the 2 aren't affected, so I'm just going to sort of separate them out as an x over 2. And then I have 1 when it's being multiplied by the 1 over n, this piece right here. And I'll do this piece, and I'll do the same thing to my n piece here. So I have 1 plus 1 over n over 1. Still in absolute values, still got the variable involved there. 1 over n goes to 0, right? So all of the piece right here, ignore the x over 2 part, but all this piece right here, which is similar to the things we've done, is a 1, right?
Yep.
We've got 1 there. So all I'm left with, since that piece is equal to 1, right, this is equal to 1, is that I have the limit as n goes to infinity of x over 2, absolute value of x over 2. Okay, so if we didn't have x and we just had a number, we would just have the answer be done, right? If x is 3, this is 3 halves, we're finished, no problem. But we don't know what x is. That's kind of the point. So as we take a look at this, do you remember when the ratio test said that things would converge?
Less than 1.
When it's less than 1. So whatever this is, by the way, I should actually have, this is just x over n, 2, sorry, x over 2. I don't have any n's anymore, so as n goes to infinity, this really just is the absolute value of x over 2. So I have x over 2 less than 1. That's when this is going to converge. I just need to solve the absolute value of x over 2 is less than 1 to figure out what that means. So we're going to take that and we're going to solve it. So what is the absolute value of x less than 2, x over 2 less than 1 going to become if I write it out?
X is less than 2.
Close.
X is less than plus or minus 2.
Ooh, can we be less than plus or minus? Do you guys remember what you do with these? This is algebra stuff from like eons ago.
2 is
It's like
less,
two different
wait, negative 2 is
Ah.
less than x is less than 2.
There we go. Okay, so it's either two different equations or you can merge them all together like Maggie said, which is nice. So when we have an absolute value that's less than an like a 1 here, we can actually separate this out to say that I have 1 is less than x over 2 is less than 1. So I do have a plus or minus 1 like you mentioned, Alex. I just have it in an inequality notation. Okay? And then I would multiply by 2, which some of you had already done when you were verbalizing it, and so I'd have it as 2. Now, that's all good stuff. That tells me the radius of convergence. What's my radius of convergence?
Negative infinity to 2, 2 to infinity.
Nope, we're overthinking it. Let me try again. Taking a look at the distance here, I've got from negative 2 to 2.
Oh, 4.
Close.
Less than 4.
Nope. Think about a circle.
2.
2. Why, Noah?
Oh,
Because
radius.
it's a radius. It's half.
Radius is halfway. Yeah, the radius is halfway. We don't want the distance completely, right? Radius is the halfway. It's from the middle to the edge. So if you take the middle of this, what's the middle of this?
0.
0. And that should make sense because where is this power series centered? At 0. So everybody make sense of this? We're connecting geometry here, like all the things. Geometry, algebra, woo, it's a good class. Yeah, Noah?
So whenever we have an interval like that, and
Yeah.
the edges are the same number, but one's positive, one's negative, that number by itself is just the radius.
It is as long as you're centered at 0.
Yeah.
Yeah, before you would like shift it if there was a shift involved, yes. So my radius is 2, that's part of the question. Now, here's the thing. I have an interval. My interval is from negative 2 to 2. We can see that in terms of the inequality notation. The problem is we have not established what happens on the edges of the interval, right? We know that sort of, we at least have negative 2 to 2, that it's the interval of convergence, but it might actually be possible that it actually also works at negative 2 and or also works at 2. So we have to test those things separately. Are you with me? So this is only part of it. We have to test endpoints. That's what we're doing, is we're testing endpoints. So we're going to test, so we at least have the interval here. So actually, let me write that down since we've established that. So the series converges. Not only does it converge, but the ratio test tells us it converges absolutely. Absolutely. For the interval -2 to 2, and diverges when x is either greater than 2 or when x is less than -2. It diverges on those pieces. But we need to test at x equal to 2 and at x equal to -2. Those are tests that we still have to run. Okay, the two tests we run are going to actually be pretty quick. When we put the numbers in, you'll see why. But I want to use my same screen so that it's all just kind of here. So I'm going to shrink this as soon as we're done with the writing. Are we good? Okay. Yeah, now it's really tiny. That's not too bad. You guys can still read it. Okay, so we're going to first test at x equal to 2. That's what I have written down first. So we're going to test number 1 at x equal to 2. So we actually take our original power series up here and we put 2 in for x. So we have the summation from n equals 0 to infinity of n, and then we have over 2 to the n, and we replace the x with the 2, so we have 2 to the n, and what does this give us?
N.
Yeah, this is the summation of n. Tell me what you know about the summation of n. It diverges. Why does it diverge, Maggie?
P series. But also, wait, not P series.
I don't think you can do
the-
P series.
Geometric.
I don't think you could do geometric.
Why?
Nth term, tell me what that one is. Do you remember?
The limit
You're right.
of something of
It equals
that
infinity.
Yeah, so,
it approaches infinity, which means
So
that.
therefore it has to diverge.
yeah. Okay, so this diverges by the nth term. Test for divergence. I'll just do nth term test. Because the limit as n goes to infinity of n, it's not 0. I mean, it's worse than that, right? It's infinity, but it's not 0. And as long as the limit's not 0, then it doesn't converge. So that means at 2, I'm still going to end up with this parenthesis here, right? It will not be able to be turned into a bracket. It does not actually converge at 2. We're going to do the same thing at -2.
We'll just do the same thing.
It will. So if we, the work looks a little bit different and the test that we're justifying it with will be a little bit different, but the result will be that it doesn't work. So on number 2, so for x equal -2, summation from n equals 0 to infinity of n over 2 to the n, and then we have a -2 to the n. So what is this series? What's the a sub n inside of this series? I mean, last time my 2 to the n's just canceled, right? I had 2 to the n and 2 to the n. I don't have that quite the same thing this time.
Is it just negative one?
We're going to have a -1.
Is it n times -1 to the n?
Yes, n times -1 to the n. Okay? The negative part of that is still going to be there, but it's not just -1. It is still -1 to the n. Yeah? Because I basically have, or one of the ways you can think about it if it's sort of tripping you up, is you can think about this as 2 times -1, and both of them have a power of n. So the 2 to the n gets replaced or gets canceled with the 2 to the n, the denominator, but the -1 to the n is still there. You good? Okay. What kind of series is this?
Alternating.
Yeah, it's an alternating series. So we need to reference that's an alternating series. What can you tell me about this alternating series? it's not decreasing, right? And that was one of my conditions for the alternating series for it to converge, is that it needs to be decreasing, and I think it said the limit needs to be 0, right? The a sub n, the 1 over a, not 1 over a sub n, but the limit of a sub n also has to be 0. So this one is by the alternating series test. Come on, get up there. It diverges. Because the limit of the part that's not the alternating part, that means of n, as n goes to infinity, is not equal to 0. So the limit not being equal to 0 shows up again, but from the perspective of a different test. And we can't just say it from the nth term test for divergence. The nth term test for divergence wouldn't work on that one because I have the -1 at the end that I still have to contend with in there, right? So all of that to say that neither of the endpoints work. So coming back up to what I'd had before, this really is my interval of convergence without the endpoints. But I can't just assume it without testing the endpoints first. It's also probably worth noting that it could be that one endpoint worked and the other one didn't. There will be problems that have that, or that both could work.
Are these like one of the things where if it does work, like you have to put a bracket? around
Yes.
it? Okay.
If it
So
had worked,
it's
we would have
included.
changed a parenthesis to a bracket. You
Okay.
got it. Okay. So case 2, when one of our ratio tests, when ratio test does this, right? Case 2 is the hardest case to do this for. We have the most work to do when it falls into case 2. And when I'm saying case 2, I'm talking about this list right here. When it falls into case number 2, we've got the most work to do. Case 1 and case 3 have far less work to do.
Was question 3 case 2?
Question 3, yes, is case 2. The one we just did is case 2, exactly. A lot of work to do. So you can see by the amount of space I gave you, the case number 4, the problem number 4 here, must not be case 2, right? Because it didn't give you very much space to write in, correct? Yeah, on your paper. So this one's going to actually be easier to do. Yeah.
So one quick thing on the last one.
Yes.
When you're writing the interval of convergence, if -2 and 2 had converged, do you write brackets?
Yes, that's what Zach was asking about too. Right. So you have 3 options or case here. So we could, well, 4, I guess. You could have had -2 to 2. That's what ours was.
Yeah.
We could have had one interval's endpoint work or
Yeah.
one endpoint of the interval work. So it would have been like that or like that. Or they could have both worked. And that's what we're trying to decide as we do this step 1 and 2 down here at the bottom and test the endpoints.
Yeah, I couldn't remember how to write it. I thought
Yep.
that was right, but I wasn't.
Mhm.
Sure.
Yep.
It's just writing the interval is just like domain notation.
Yep. Same as domain notation and range notation. Yes. Okay. Let's take a look at this one. Again, direction's the same, radius and interval of convergence. Still using the ratio test now. I know you have to leave, but you'll check it out later. It'll still be the ratio test when you do that too. So we're going to use the ratio test. So we're going to have the limit as n goes to infinity. And I'm going to write the original part. You don't have to write that part each time, but it's a sub n plus 1 over a sub n as a reminder. All right, so we have, let's see, we've got k in this one. So, they're not n's, they're k's. Well, I should probably make them consistent, I suppose. Some of you are like, no, I don't want to do that. Okay, these are k's. All right, one more. All right, so I have k plus 1 factorial. I have x plus 1 to the k plus 1. I would be over k factorial and x to the k. Notice this is not centered at 0 anymore, right? This is centered at -1.
Wouldn't it be x plus 1 to the k in the denominator?
Yes, thank you. I see what you're saying. It took me a second to realize what I had messed up on. Yes, you're right. It is x plus 1 to the k. Thank you. In my mind, I was thinking about the plus 1s from the exponent part, and I left it off. Yeah. Good deal. All right, we're gonna simplify some stuff. Somebody tell me something we can simplify.
The k plus 1 factorial and k factorial.
Okay, how will those simplify?
2k plus 1.
Yes, very good. K plus 1 on the top. Wonderful. How about the other piece? Will it simplify?
S plus 1 to the k, x plus 1, k plus 1.
Okay, so what will it look like?
Is it just x plus 1?
Yeah, so we'll have just an x plus 1 on top. Okay, very good. So these are going to condense and simplify down. That's how the ratio test is going to work for us each time. So this is the limit as k goes to infinity. And we have k plus 1, again, absolute values, times x plus 1. So I didn't actually draw, like, as in pull out this last time, but I want to show it to you here as well because it's sometimes easier to think about it. It looks like we're still trying to plug the infinity in for the k, but there's an x in there too that's not affected. So you can think about it as the x plus 1 being sort of in front of the limit notation because it doesn't affect it. And then we have this piece as k plus 1 inside. Okay. So then, what in the world is the limit of k plus 1 as k goes to infinity? That's infinity, right? That's infinity. So you might say, well, then what's going to happen here? Because you told us that it didn't have a divergence option, right? Case 1, 2, 3, none of them really diverge. So here's what happens when you get infinity here. There's two options. One is that the answer is infinity. Obviously, that would be divergence. That's not cool. But there's also a possibility that the limit is actually 0. Take a look at the entire expression here and tell me if you can, what would make this whole thing be 0?
When x was 1 over infinity.
Nope. But you're right about the fact that it's going to involve x.
K.
Nope. These two pieces, let me separate this out this way. These two pieces are being multiplied, correct?
Yes.
X negative 1.
There you go. So if the first piece actually had x is equal to 0, right? Not x is equal to 0, but the whole piece is equal to 0 is what I meant to say. Everything I just circled was 0. It would zero out the limit part as well. Does that make sense? Because a piece of it would collapse. So if my x value is equal to, in this case, negative 1, it zeroes out the part that's in the beginning, which would zero everything out. It would be 0. And if it's not equal to negative 1, it's infinity. Can you tell me which case I'm in? Can you tell?
The first one.
Yeah. This is case 1. One more back. Case number 1. It will converge, but it only converges at one single point, the point that makes it all zero out, right? The very uninteresting one. It's a collapsible kind of an image. So this converges. For x equal to negative 1. What's the radius? 0. Okay, that was over here. It talked about the fact in this definition that if you, in case number 1, the radius is 0, because it's at a single point, right? It's a collapsible interval, so it's a single point, so the radius is 0. And there's no interval of convergence. No interval. Because it's at a single point. And a single point can't create an interval. So we all like case number 1. It's weird feeling, but it's a whole lot less work. Yeah? And a very similar argument would result if we were working in case number 3. If you were working in case number 3 and you got to the point where it's converging everywhere, then you don't have to test endpoints either, right?
The limit equals 0.
Yes, if you had the limit equaling 0. Yeah, so exactly. So if this part that is in parentheses over here had actually a limit that was equal to 0, instead of it being another number like we had the last one was 1 instead of like 4 or something like that, if this were 0, then it wouldn't matter what this is. The limit would still be 0 here. So, very good note.